Hello. Okay. I want to thank you all for coming tonight. You are the hardcore people. A lot of other people are out drinking, but you came here to listen to me talk. My talk tonight is about how to make your software perform well, subtitled Optimization of GNU Linux Code. Now, a lot of you have been coming here to Latinoware and listening to me for a very long time. Or you've gone to other conferences and hear me talk. And you think of me as that nice old man with the long white beard that goes around giving away free software. Ho, ho, ho. And of course, I give away the free software to good little girls and boys. To the bad little girls and boys, I give away Microsoft. But I have been lots of many things in my career, and one of those things is a programmer. And I've also been a university educator. And because of those two things, I've always had this love of computer architecture. Now, in May of 1994, I met Linus Torvalds for the first time. And I gave him a 64-bit Alpha computer. That was also a RISC instruction set computer. And those two things were very important because I wanted Linux to be a platform where you could create new algorithms to use in a very large address space. You'll find, as you study computer science, that there are some algorithms that work in a small address space, and sometimes you have a trade-off between the processor speed and the amount of memory which you have. And with the more memory, a lot of times you can have a different algorithm which will give you a much greater speed. Now, the other reason I gave him the Alpha was because it was a RISC processor. And there were two main types of processors in the world. A complicated instruction set, like Intel and AMD, and a reduced instruction set computer, such as the ARM chip or the Alpha. Now, I've been in the computer field since 1969. I've worked in a wide variety of different architectures. And I'm sorry, Intel, but I think that reduced instruction set is the way to go. And so I wanted Linus to make sure that Linux was portable to many different types of architectures, not just Intel. Now, a little bit later, I also took on the role of being the executive director for Linux International. So I left my company, Digital Equipment Corporation, to work on free software full-time and to promote Linux worldwide. Now, why am I doing this particular talk tonight? It's because over the years, I've heard people say disturbing things. They said, CPUs are fast enough. Now, I've been in the computer field since 1969, and every 3 or 4 years I'll hear people say, wow, CPUs are really fast. They're doing 1 million instructions per second. Wow, CPUs are really fast. They're doing 10 million instructions per second. They're doing 1 billion instructions per second. They have 2 cores, 4 cores, 8 cores. We're always looking for faster. If anybody ever tells you that CPUs are fast enough, please tell them to go to the back of the line, to the end of the class, because they're never fast enough. And they won't be fast enough until I can talk to my computer system and they can understand me the same way that you understand me. Or maybe you understand me through the interpreter. But that's the only time they may approach the speed that I want. I have another disturbing thing I hear, and I hear this from college professors. Java is the only language that people need. Java is the be-all, end-all language. I will believe that when Larry Ellison rewrites the Oracle database in Java. After all, Oracle owns Java. If Java is such a great language, why don't they write everything in Java, including the Oracle database engine? When that happens, there's a place called hell, which will freeze over. Nobody codes in assembly language anymore. This is another thing I hear from universities. Nobody codes in assembly language. Well, it's true. If I had a programmer who wrote large programs only in assembler language, I probably would fire them because they're taking too long to write something which there are good high-level languages that will write it as efficiently or better. But you need to know the architecture of the computer to be a really great programmer. And that means that you have to know something about assembler language. You have to know something about what a register is. You need to know something about what cache is, cache memory. You need to know that the disk rotates and has an arm that goes in and out, and that tapes start and stop, and mostly stop. These are the things you need to know and understand to be a really great programmer. And people say, oh, Maddog, virtual machines and abstraction make all of that go away. No, they don't. They only make it harder for you to really know what you're doing. And the person who actually understands machine architecture will be able to write really good programs. Now, when I do programming, I tell people I do real programming with real data, with real problems. I don't write little games. They don't interest me. I don't write little GUI programs. They may interest other people, but not me. If it's not petabytes of data, if it's not thousands of cores in the problem, if it isn't multi-levels of programming, I'm not interested. It's not interesting to me. And so, I need to know about the architecture of the computer. There are some people who need to know about real time, and therefore they need performance. And in doing real-time programming, you need to make sure you're using every cycle that you can. Now, what am I talking about real time? Back in the days when I started programming and computers were executing tens of thousands of instructions per second, you would make a decision about what type of a lock to use to keep your threads of code separate from each other. Because a spin lock may be the only one that was fast enough to allow your program to work. Setting up a semaphore took too much time. But today, when your instructions are executing in billions of instructions a second, to not use a semaphore is something that is bad. So, you need to know about the architecture of your system, and you need to know, is it real time enough? Real enough. So with very fast processors today, even an operating system like Linux can handle most real-time applications. Not the realest of real time, but almost. And so you can write real-time applications using a Raspberry Pi, for instance. It'll handle it. Most of them. Some of them you need an Arduino. This is something you have to understand. You have to know what it means. So one day I was talking with Linus on the phone in the early days of Linux. And I said, Linus, you need to make the soft real time of the Linux kernel better. We're losing a lot of business because the kernel is not real time enough. He goes, what do you mean? He says, it's real time enough. He says, when I'm playing Quake and the monster has a gun in its hand and I hit the button, I kill the monster. That's real time. I said, Linus, put a real gun in the monster's hand and see if it's fast enough. He thought for a couple seconds. He said, I see what you mean. And the next version of Linux, the soft time was much better. If your nuclear power plant is melting, you don't want to be using Java to stop it. Because in the middle of Java executing, it's going to want to stop and do garbage collection of memory. So, nuclear power plant starts to melt, Java program says, lower the... Oh, wait a minute. I have to do garbage collection. Collecting garbage, collecting garbage, collecting garbage. Oh, okay, finished collecting garbage. What was I doing? Oh, what happened to the power plant? It's called Chernobyl. It's gone. That's not real time. When your nuclear power plant is melting, you forget about garbage collection because if you go and do it, there won't be any garbage to collect. Everything will be gone. Real time. What about cell phone applications? Hey, certainly CPUs are fast enough for cell phone applications. Why should you try and make your application run any faster? Well, it's not so much that the application has to run any faster, it's that you want the application to go into sleep mode faster, so that your CPU and your operating system can go into low power mode faster to save your battery. And so, performance on a cell phone, for the most part, is about saving battery, making your battery last longer. Saving the environment. Let's take that concept of your cell phone and let's apply it to that server system that the guy from IBM was just talking about. All those thousands of processors. If you can make your application more efficient so those thousands of processors can finish their job faster, then the supercomputer can use less power. Your server system, all the applications running on it, if they run faster, they'll run more efficiently, they'll use less electricity, and will save the environment. Because let's say there's 1 billion desktop systems, actually there's 2 billion in the world. If each one of those 2 billion systems save 7 watts of electricity during the day, they actually save enough energy to equal Itaipu, 14 gigawatts of electricity. So, if we can make our systems more efficient and still get our jobs done, we save the environment. And it isn't Itaipu that the power company will turn off. They'll keep Itaipu running. Why? Because it's green energy. The systems they will turn off burn coal or oil or some other type of polluting energy. They are less efficient. Those are the ones that the power companies turn off first. Finally, there are new processors that are coming out. Not the traditional CPU with single core or even double core or quad core, but again, as a gentleman from IBM was talking about, multi-levels, different types of architectures, field programmable gate arrays, digital signal processing chips, multi-core CPUs. And you need to know the architecture of how to program this. Compilers will do a certain amount of the work for you, but there's only so much the compiler can do without you, the programmer, giving it hints, giving it direction, and helping it do its job. So, the first computer I ever programmed was an IBM 1130 computer, which had 4,000 words of memory, and I programmed it in Fortran. That was when Fortran was spelled with all capital letters, It wasn't Fortran 2, wasn't Fortran 4, wasn't Fortran 77, wasn't Fortran 90, wasn't high performance Fortran. It was Fortran because that was the only language we would ever need. Except for the second language I learned, which was assembler language for the PDPA computer, which, by the way, was in fact a RISC computer. A computer so simple, you could not even subtract. You had to take the 2's complement of the subtrahend and add that to the minuend to get it to subtract. The translators are probably having fun with this talk. So I learned to program this from reading a book, because you know something? Nobody told me that assembly language programming was hard, because it isn't. It's just another language. Yes, you have to know something about the architecture, but all the things you learned in your other languages apply. So, you learned about assembly language. Now, how does that help you in today's world? Because if you're trying to write in any high-level language, understanding what the compiler is doing underneath is useful to you. It helps you write your code so it works better. Working right out of my university at the world's largest insurance company, Aetna Life and Casualty. In 1973, we had a 3-acre computer center. Imagine this room 20 times the size. That's how big our computer center was. And we automatically ordered everything, 2 of everything that IBM announced. No salesperson had to call us. IBM announced it, we had 2 headed our way. We had 500,000 magnetic tapes in our tape library on site, and another 100,000 tapes in a salt mine in Idaho. And we had one system that had 500 disk drives hooked up to it. Each one of those disk drives cost $32,000 US in 1973. To give you an idea, my family bought a 3-bedroom house on a 1/4 acre of land for $32,000 the same year. So imagine that we had 500 houses sitting in our computer floor. Now, I was an assembly language programmer, and I would write my programs in assembly language. But we also had COBOL programmers. And the COBOL programmers would go and write their programs in COBOL. And one day, one of them came to me and said, "John," I wasn't known as Maddog in those days. He said, "John, I can't figure out what's wrong with my program. Would you look at it with me?" And I knew COBOL, so I started to look at it. And I said, "I don't see anything wrong with this program." He says, "I know, I don't see anything either, but I'm still getting the wrong answer." I said, "Maybe the compiler is making a mistake." "What? The compiler making a mistake? How could that be?" I said, "Because the compiler is a program, just like your program. It was written by a programmer, just like you. Maybe the programmer had a bad night before they released the compiler. Maybe they were drunk the day they were supposed to test it. Maybe they didn't test it at all. And so we would turn on a switch on the compiler to generate the assembly language. And I would go down and say, look, right there, it's not generating the right thing. And so we would have to go back and fix the compiler. Yes, we had all the source code to the compiler because Aetna was a large enough company that we demanded to have the source code for everything that we bought, even IBM's operating systems. Another time, I was working on a program, and my job during those days was to make other people's programs run faster. That's literally what my job was. And I would go in and look at people's programs that were running slow and figure out why they were running slow and make them run faster. There was this one program that it ran very slow. Not only did it run slow, but when it was running, every other program on the system also slowed down. Not only did that happen, but every program on every computer, even remotely attached to this computer, would slow down. And my boss came to me and he said, I don't know what's going on, but whatever it is, it's pretty horrible. Would you fix it? Okay. So I ran what is known as a profiling program, and I found out that one machine language instruction was using 99% of the wall clock time. And so if the program ran in 100 minutes, this one machine language program was using 99 of the 100 minutes. One instruction. And so I looked at the instruction and I said, what is this? And the instruction was, reads the clock. That seems to be a simple enough instruction. It seems to be a passive enough instruction. What is going on? And then you read a little bit further down and it said, this instruction is being used to synchronize symmetrical multiprocessing on the IBM system. And so every time that instruction was being executed, all the input-output of the IBM system had to come to a stop. All of the cache in all of the memory had to be flushed. All the registers had to be written out. Everything had to come to a stop. And then the clock was read, because this was used to synchronize all the other CPUs attached to this program. And then when the instruction was read, everything would start up again. And I went to the programmer and I said, why are you reading the clock 200,000 times during your program? He says, I want to figure out what day it is. I said, why don't you just read the clock one time at the beginning of your program and store it in a variable? He says, oh yeah, I guess I could do that. And we changed this program and recompiled it and put it back. And all of a sudden this program went from taking 10 hours to taking 10 minutes. The operators thought that the program had come to an illogical termination because it ended so fast. IBM also had this very nice code set called EBCDIC. It's something like ASCII, except it's kind of like ASCII done wrong. And EBCDIC had these 4 instructions in assembler language, which were the 4 slowest instructions on the IBM mainframe. One was to take EBCDIC and convert it into packed decimal. Another one, packed decimal into binary. And then the 2 opposite instructions, take binary, convert it to packed decimal, and packed decimal to EBCDIC. You do not want to store an index to an array as an EBCDIC number, because every time you use it, you have to go through those 4 steps, the slowest ones on the machine. If you simply stored the number as a binary number, those conversions would not be necessary. Unfortunately, in the COBOL language, it was real easy to store it as the wrong thing. And because the COBOL programmers didn't understand what was happening in the machine, they often did the wrong thing. I had a friend of mine named David Mossberger Tang, who helped with the alpha port. And he wanted to multiply 2 very large arrays together. If you do this, like most people would after learning algebra, you take the first array and you go down the rows of the array, taking up numbers, and then you multiply them times the rows going across in the other array. In the first array, every number you pick up tends to stay in the cache memory of the computer. In the second array, every number you pick up tends to miss the cache, which means you have to go all the way out to the main memory to get the number to do your multiplication. So David figured if you first took the time to take the second array and invert it, then you multiplied the two arrays together, and then you inverted the answer, you got the same result. Except on the Alpha processor, the multiplication went 40 times faster. On an Intel processor, it typically went 10 times faster because the Intel didn't have as much cache as the Alpha did. David understood what was happening when he was accessing these numbers. He understood the architecture of the machine. I was at a small school. We had a PDP 1170 computer, and we had a program that had been written by a programmer. It sorted 1,206 32-byte records, a very small amount of data by today's standards. But the program he wrote knew nothing about the architecture of the machine, and it took 10.5 hours to sort those records. I rewrote the same program using a different algorithm, and I shortened the time to 3 minutes. Again, it's because I understood the architecture of the machine. In the early days of the X Windows system, the engineers at Digital were using the GCC compiler to write the X server. And Digital had a very good optimizing C compiler. The GCC compiler of those days was not as good at optimizing as it is today. So my company said, what would happen if we took our C compiler and compiled the X server with it? We should see perhaps a 30% improvement in speed. So we did that. We saw a 0% performance improvement. Nothing. Why? Because the engineers who were using the GCC compiler understood the compiler so well and knew what type of code it would generate that they actually changed their code so the GCC compiler generated code as efficient as the VAX C compiler. They understood the architecture of the machine. And finally, when you're working on programs, you have to think about the balance of the CPU speed, the memory speed, the cache speed, the I/O speed. It doesn't do you any good at all to try and get more CPU performance out of a system whose I/O bandwidth is not going to allow you to get the data you need. So you need to know how to balance all of these things. So today, what most college students are learning is Microsoft and Oracle instead of Office systems and databases. We all know that that is bad. But what they're also learning is Java and TI, or information technology, instead of assembly language and how operating systems work. Not every university is teaching this, but enough. And we have to stop this. We have to stand up and demand that students who are learning computer science learn real computer science. A lot of high school students get a computer from the store. They don't get any compilers to go on them. And they go home and they put a game on them, and they write some HTML code, and they think they know how to program. And then these students are now going into universities. And the University of Cambridge, for instance, was seeing students come in who thought about computers like this. Yeah, computer's my friend. Little funny little computer thing. I play a game on it, I write some HTML, I'm a programmer. And what the professors at the University of Cambridge said was that this is really how computers look, and that they were finding incoming freshmen who knew less about computers, who knew less about computers today than the students of 20 years ago knew about computers. Because the students of 20 years ago would get a computer that had no operating system on it. And they would have to type in programs that they got from magazines and bulletin boards. And sometimes those programs would have mistakes in them. And the students would have to fix the mistakes. But today, the students would go get a box of games off the shelf in the store and play them. That is not computer science. So the university professors got together and said, we're going to create this little computer called the Raspberry Pi. Another example of this is a friend of mine has a small company where he hires programmers. And he said to me, Maddog, I just interviewed this person. Then when I said, do you know what computer cache is? He said, yes. Somehow it makes the computer run faster. This is not the person you want to hire. So the University of Cambridge created the Raspberry Pi, a computer that is so inexpensive that every high school student could afford to have it. A computer that's outside of the box, doesn't have a case. A computer that you really have to know the metal of the machine. And they want every high school student to have one of these to be able to practice what they call real computer science. Well, I think that this is a wonderful machine for high school students. However, I tend to think that it's another machine, much more like this one, that university students should have. This is a machine that's being designed by a company in Littleton, Massachusetts, that is basically a supercomputer on a card. It has a lot of the features that the IBM systems were talking about. It has a two-core ARM processor. It has a field programmable gate array, known as an FPGA. It has digital signal processing chips. And it has a 16-core CPU, where each core has its own megabyte of memory that you can load and have it programming in parallel. This board only US. Now, the company that makes this is very happy to license this out, to have it manufactured in Brazil, and I am negotiating with them to do that. So you will be able to have it at $95 instead of twice that because it's made outside of Brazil. I'm not advocating you buy this board, but I am pointing out that these type of boards are becoming more and more available at a lower and lower price so that you can do sophisticated programming. But sophisticated programming means that you're not programming in Java. You cannot effectively program this board in Java. And I don't think that Java is the primary language on the IBM supercomputer. Am I correct? He's shaking his head, yes. So what I'm doing today is I'm pre-announcing Maddog and Lineo's GNU Linux optimization program. The ARM processors are designed by a company called ARM that exists in Cambridge, England. But ARM does not manufacture the CPUs. They only design the architecture. Other companies like Hitachi, Samsung, Broadcom, I'm not sure if IBM does any ARM processors, but they do PowerPC, which is a good CPU. And these other companies produce these ARM processors and put them into systems. And so a lot of the telephones that are Android or iOS or ARM processors, you may have ARM processors in home routers, lots of things that use a very small amount of power and don't generate a lot of heat. But a lot of these companies that produce this also want Linux to work on them. And so Linero is a company, it's an association of companies that make sure that Linux works well on ARM processors. And companies like Texas Instruments belong, and Hitachi belongs to Samsung. ARM is producing a new 64-bit chip. It has a 64-bit address space, just like the Alpha had a 64-bit address space. And they found out that 1,400 modules inside of GNU Linux have assembly language in them. This means that 1,400 programs would have to be ported to use the ARM 64-bit system. They said, oh man, that's a lot of programs. Maybe we can get the community to help us port those programs. But porting is not very interesting work. It's kind of grunt work, not very fun. Because you have to port, then you have to test, stuff like that. But we started looking at these programs a little bit closer. Some of these programs were written a long time ago. Some of these programs were actually written 20 years ago. They were written when memories were very expensive. You couldn't get a gigabyte of memory for $10. They were written when most of the CPUs were single core. A lot of them had an Intel assembly language in them, and the other assembly languages were just kind of copied, instruction by instruction. This is not really the way you should do it. And these programs were written when the GNU compiler suite didn't have as many optimizations to it. It was less efficient. Some of these programs were written to find out information about the computer. They would probe the computer to find out what type of computer it is. We feel that this type of thing should be done in what is called a compiler intrinsic, not by writing assembler language. And so, in looking at these, we said, maybe some of these programs should not have assembler in them anymore. The reason for writing the assembler is gone. Maybe we should allow the compiler to generate the code and never have to worry about assembly language again. Maybe we should look at the entire program, and maybe there should be an algorithm change to make the program run faster. There's lots of things that can be done with these programs to make them run faster. And if these 1,400 programs ran 2% faster, 5% faster, or 7% faster, then the entire operating system would run faster. You might find your battery would last 7% longer on your cell phone. Or you might have a new algorithm that could change it and make the program run 10,000 times faster because you decide to use more memory because you realize this program is on a server system. Maybe you can change the program to use multiple cores, do things in parallel. So we decided to change the direction of this from being just a porting issue to being an optimization issue, and to go through and to document the changes that you make and the optimizations that you do. So what types of categories of optimization will we look at? How much faster is the program now than before you started? What percentage change in the speed can you measure? Also, how do you utilize memory? Remember, a lot of GNU Linux systems are embedded systems. You don't want to use a huge amount of memory for a small performance improvement. But if you're on a server system, you can justify using a much larger piece of memory if you can get a 50% performance improvement. Cache utilization. How do you utilize the cache of the machine to make your system run faster? And finally, the best algorithm replacement. Can you find a new algorithm or an algorithm somebody didn't think of to make the whole process run faster? And we want whatever changes you make to be acceptable to the upstream developer or maintainer of this program. So you would have to work with them. Now here are some of the suggested prizes that we have. We are going to be coming out with ARM development systems for 64-bit. So you may be able to win a nice 64-bit ARM development board, which typically costs several hundred US. We have these meetings 3 times a year called Connect. And in these meetings, some of the best developers in the world come to these meetings to interchange ideas. The last one was held in Dublin, Ireland. We had 350 engineers show up, exchanging ideas, talking to each other, drinking a lot of Guinness. It was wonderful. The next Connect is going to be held in Santa Clara, California next week. The Connect after that will be held someplace in Asia. Could be South Korea, could be China. And then we go back to Europe. So if you win the contest, you will get a chance to go to a Connect meeting and to talk about what you had done to all these engineers and to have their input and stuff. And these people work for some very influential companies. You might find that you get a job offer from Samsung, or a job offer from Hitachi, or a job offer from IBM because of the work you do in this place. But even if you don't win, what else might you get out of this? You are going to learn a really interesting machine language. ARM is a very nice, very clean type of machine language. It's useful for you to learn it. You're going to learn how to do code analysis and code analysis techniques and how to measure the performance of your programs. You're going to learn how to create better code overall by knowing how the machine works. And you can put all of this into your open source portfolio that you take to a potential employer to say, this is what I did. This is how I coded. This is how I worked with the upstream developer. These are real life skills that will be much more impressive to a potential employer than having written some crazy game. Unless, of course, you're going for a game job. We're going to try and take a lot of the output of this and turn it into a university level course in optimization, so that universities will be able to teach this to their students. And you also get a chance to do research into new optimization techniques, such as automatic detection of race conditions, which is something that people are doing investigation into. I missed the remote changer in this thing. So the time frame of this is we're now formalizing the final program, doing the final steps of this, and in the next couple of weeks, we're going to be announcing this as a contest. We're searching for universities that wish to work with us on this to basically guide and to store the information that we generate out of this. We're going to publish everything that we learned from this optimization course, and we hope that one of these universities will actually pick this up and develop it into a course they can teach their students. We're going to publish all of the rules, the prizes. We're going to give examples of code, and that'll all be done in the next couple of weeks. We're going to end the formal part of the contest by 2014. The earlier you get involved, the more likely you are to win one of the trips to Connect. If you wait until the end of 2014, you may only win a chance to one Connect. But if you do this right after we announce it, you'll be more likely to win at least one trip to Connect. So details on this are coming. I have a blog at Linux Pro Magazine. We'll be announcing it there. So keep an eye on my blog. I also do an announcement to my Facebook page and through Twitter. And if you want to get started, you can start looking at some of these resources. There's books on the GCC compiler that talk about the different optimization techniques. You should start studying them. You should start studying the techniques that are specific to ARM. You should also look at debugging and profiling programs. Become familiar with them. And finally, you should start looking at the ARM language. And that is best specified by this book, the ARM assembly language. Now, a lot of this information is available free at the Linero site. You can go to the Linero website and find information about their architecture, or the ARM Corporation. They have emulators already existing for ARM64, even though the hardware is not ready at this point to distribute. So you can start to do your optimization now and submit it as you wish. So that is the end of my talk. And if you have any questions, I'd be happy to try and answer them. I have my headset. If you're going to speak to me in English, please indicate that. If you're going to speak in Portuguese, give me a second to put my headset on. Thank you very much. I think I saw a wave back there. That's cool. Thank you. I will be here all day tomorrow anyway. If you want to come up to me and ask me questions about this, that's okay too. Any questions? Over there. And I see a hand up over there too later on. Okay, you're not wearing a headset, so I'm seeing you can talk to me in English. I don't hear a word. Oh, I just heard beep. Okay.
I see you put your blog in there, but I want to know how to do to describe my college in it, the project, to optimize.
Okay, your college, so this is part of what we're going to be publishing in the next couple of weeks, are the exact steps to joining the contest and to get your college involved. So the first thing you should do is go back to your college and talk to your professors and tell them about this contest. I have actually had professors come up to me and say, I would like my students to be involved with this because I'm teaching assembly language and I'm tired of giving my students stupid programs that they'll never use and have no effect when I can give them this, which is a real life example of work that they would have to do. So the professors in teaching assembly language want to give some of these modules as examples to their students to do kind of like homework. So this is one idea that some professors have had. But we're not going to stop with the 1,400 modules. These are only modules that have to be ported. We want to continue the performance part of this contest to do all of Linux.
Like a new system?
It's not a new system. It's going through the code and trying to make it more performance conscious, given the fact that the architecture has changed over the years. Memories are larger, CPUs are faster with multi-core. We should be looking at this and taking advantage of it. This is something that a company like Microsoft can't afford to do because they have to make a profit. We have an unlimited workforce, okay, that will work on this because they want their system to run faster.